Very good morning. So, day two of the faculty development program on automation, leveraging IoT and AI, artificial intelligence for automation. So, I welcome you all. And today's chief guest is Professor K.R. Guru Prasad. So, he is from Indian Institute of Technology, Kanpur, and currently is also the visiting professor at IIT Madras. So, welcome, you sir, and thank you for accepting our invitation. I think spontaneously accepted our invitation in within minutes, and this was way back 6 months back when I approached him, and today he's here along with us. I thank you. Along with us, we have Professor Melvin Joe Thomas, who's from IIT Suratkal. So his session is in the afternoon. He's also present here. I welcome you, sir, for this FDP, and welcome all the participants, and I request my colleague Professor Ratnakar to give a brief profile introduction to today's chief guest, Professor Guru Prasad.
Thank you, Professor. Very good morning, and welcome you all to the second day's sessions. It gives me immense pleasure to introduce you, Professor Dr. K.R. Guru Prasad, Associate Professor, Department of Mechanical Engineering, Indian Institute of Technology, Kanpur. He is also serving as visiting faculty, Department of Engineering Design, Indian Institute of Technology, Madras. So he had his PhD in the domain of aerospace engineering from Indian Institute of Science in the year 2009. Then he has his MSc Engineering from Indian Institute of Science, Bangalore, India in the year 1996. BE in Mechanical Engineering from Bangalore University, so Karnataka Regional Engineering College, now which is called as NITK, Suratkal, in the year 1993. So currently he is working as visiting faculty, Department of Engineering Design, Indian Institute of Technology, Madras. So he has a very wide experience. From 2022 to current, he is working as Associate Professor, Department of Mechanical Engineering, Indian Institute of Technology, Kanpur. So 2002, June 2022, he has worked in the Department of Mechanical Engineering, National Institute of Technology, Karnataka, Suratkal, India. 93 to July 94, training engineer at BPL Electronics Limited, Bangalore, India. So March 2011 to May 2012, postdoctoral fellow visiting researcher on sabbatical, computer science department, University of Nebraska, USA. So he has worked in the domain of autonomous sensor-based single robot motion planning, multi-robot coverage path planning for landmine detection. So its research interests are in the domain of robotics and automation systems. He has worked in the area of motion planning, signal and multi-robotic point-to-point motion planning, coverage path planning, robotic exploration and mapping, etc. So he has also worked in the domain of UAV drones, single and multi UAV motion planning and control, multi UAV search and rescue, multi robotic agent systems, deployment, cooperative and distributed control, emergent behavior, mobile manipulation, artificial intelligence. He has worked in the domain of artificial neural networks, fuzzy logic and fuzzy logic control, intelligent control, reactive or behavioral based systems, group behavior and distributed systems, etc. So he has also worked in the field of robotic mechanics and control, manipulator control, distributed control, control of lower body and whole body exoskeletons, etc. He has lots of publications. So its H index is 14, eigen index is 21, citations are around 665. So he has published a lot of papers in journals, more than 22 papers, okay, book chapters, conferences, okay. He has also authored textbooks, okay, in the robotics, in the domain of robotics, mechanics and control. One more book, Smart Sensors, Measurements and Instrumentation Selections, okay. He has given a lot of training of researcher students, completed more than 5 guided 3 doctoral students, 2 master of thesis, etc. So he has a very wide experience. He has received award fellowship from Indian National Academy of Engineering (INAE). He has received best paper award, best presentation, etc. So we have a very distinguished personality here with us. I welcome you, sir. On behalf of the participants, I extend you a very warm welcome, and we look forward to hear from you. Thank you.
Thank you. Okay, so thank you for that kind of introduction. And thank you, Vijay Kumar. I know only him and his team. I mean, there is a lot of team members with whom these things happen. I mean, I had actually done a similar kind of FDP during my initial career. So I know, I mean, it's satisfying at the same time, it takes a lot of effort in organizing and getting the funds and things like that, in fact, in getting the participants too. And I thank all the participants who are physically present here, because nowadays a lot of things happen online. So he specifically mentioned to me that, because when he contacted me, I was in Kanpur, but I had plans of coming to IIT Madras. So he insisted that it has to be a face-to-face presentation. So that is good, because now this online or virtual, whatever you want to call, that doesn't connect. So I feel like I'm talking to my laptop, and you feel like you're listening to a broadcast. Right? So though it is live, but still. Okay, so I am not talking directly about, I typically am not used to speaking to the mic. I just want to move around. Let me see. In between, I try to move around, and probably my voice is loud enough so that you hear. But maybe I'll start from here. I think you had wanted to give me that. Yeah.
It will catch. But if you want to
No, but you wanted color mics for some other purpose.
yeah, like yes.
Fine. Okay. Okay, so this is kind of what I'm talking about today. There are actually 2 topics combined. Both of them actually are related to motion of a robot, and there is planning involved. So I have combined them. In fact, this is basically a chapter in my textbook that was introduced. It's a standard, typically all engineering curriculum will have a robotics curriculum, right? So this, and robotics, basically when you teach as a first course, you teach a serial link manipulator. You want to know its kinematics, position, velocity, and then dynamics and control. Basically this book is about that. I'll mention about that later. And in such a course, typically we don't teach so-called motion planning, but we'll talk about trajectory generation. Okay. So this actually contains both of them depending on your interest, what you're looking for, and what is how much time we have. So I will modulate. I may not go exactly according to whatever I have. I put it here. Okay. Fine. The idea. Am I audible from here? Yeah. Okay, fine. So basically, this is taken from a classical, I would call it classical robotics book, okay? But nowadays, by default, when we say robotics, people think of mobile robots, okay? So when it is mobile robotics, it could be moving on the ground, a wheeled or any other mechanisms. It could be UAV kind of thing, which is a flying robot, or it could be underground or surface vehicle. All of them have to move. Okay, so some of the slides are made with perspective of manipulator, but we are not restricting to manipulator. One part of it that we are talking about is more related to manipulator. The rest are more of so-called mobile robotics. Okay, so in what is a robot? What is a robot? Can we actually, this is an impromptu discussion, no slides on that. What do you think a robot is?
Manipulator perform the task based on the program.
Okay, so he says it's a manipulator, right? Performs a task. So what is a manipulator? Why it is called manipulator? Any? So I'm in a classroom mode. So this is supposed to be a kind of classroom. So it's not a lecture. Okay. So I'll be in between. Certain things will be more of a lecture kind of thing. Certain things will be more of a, So I'll come back to robot. So why is a manipulator called a manipulator?
Because it's an electromechanical device.
No, let him. Sorry, I'll come back to it. Yeah.
Performs the task in the performs like the pick and place.
Partly good.
It's a final control element. It's performs the task.
What is manipulation or what is manipulator? Basically, you take something and move it around, something else. So if I move this tape, if I move this is a manipulation. If I do like this and change its position and orientation. Not the robot itself, something else, we typically call it a workpiece in context of industries. But nowadays, these traditional robotics were initially from the perspective of industries, right? To do human-like operation. So a manipulator is basically copy of human arm, right? Yeah. Okay. So robot is basically a machine, right? But what is the fundamental difference between a robot and a machine? Any other machine?
Multifunctional.
Nowadays, that is correct. Your definition was correct. But you can have multifunctional machines nowadays. It is very important keyword.
Orientations, or it can perform any.
But why do you put it as a separate thing, not just a machine? Robot is just a machine. Nowadays, all machines are programmable. Yeah. CNC is basically programmable.
Without human intervention.
That is automation. Right, so that is an important keyword because it has to be automatic, right? But there are a lot of automatic machines, including our washing machines is automatic now.
It provides mobility. Mobility of one.
A crane also does that.
Human-like.
Or human-like. If you look at the history of robotics, what is the word robot mean? This is introductory material somebody else might have covered. But I need some introduction, some understanding so that, I can get into that. So it might be repetition. So it is human-like. Basically, what does the word robot mean? It's a slave in some Czech language, right? Where I think it was, what was his name? Karl Capek, right? So it was basically from a science fiction where he made an artificial human. Okay? And basically, you can coin terminologies in science fiction. It should sound scientific. He called something protoplasm is basis of, like in Indian context, we say Atma is the basis of, or Chaitanya, Chetana is basis of, life. So similarly, from scientific perspective, so maybe you could call it DNA or something like that, but he called it protoplasm. He created artificial protoplasm with which he created. See, these Westerners were always worried about slaves, right? So they want somebody to do their job. So getting human slaves is difficult. So they wanted to make a machine which is a slave. So they did not make a machine, they made artificial human being, which is a slave. So from that word came. To do justice to that, even in our thoughts, whether your books say or not, my book says that, whether your books, because books do not want to give that definition because it doesn't look formal. Okay, so whatever is robotics, in your mind, robot has to do with something. So you might say this mobile robot doesn't look a human being at all, but there is a concept of moving that comes from animals, right? So there is an engineering innovation. For example, in Gujarat, there is a science museum, I don't know what exactly it is called, and there is a robotics, this thing, so it's very nice. and there is a small restaurant, very small cafeteria kind of thing. They have a service robot. Okay, it looks like human being, but it actually moves with wheels. But bodily, it looks like human being. So you get a human-like feeling. So that is why it is a robot. Okay, but just because I move like this, because no, oh, I'll come back to you. Just because I move like this, and just because nature doesn't have wheel, nobody stops you from. So you want to move. You want to copy the idea of movement. The movement of a machine and the movement of human beings are slightly different, right? Of this thing, it will entire body will move around. Most of the machines do not. So car is a machine, so that we can talk about whether autonomous car is a mobile robot. That's a different question. Let us not get into that detail because we have to cover other stuff. Okay, this motivation from not only from human being. Now you have dog robot, you have insect robot, you have ornithopter, which actually kind of. You have typical in aircraft kind of thing, flying machines. You have fixed wing aircrafts, you have quadrotors, none of them are human-like. But you have flapping wing. They are actually trying to copy, but you don't just copy. Why do you copy? Because the nature has optimized everything so much. So it has solved your, in an engineering, what is engineering? Engineering is basically using our knowledge to design some device, right, to perform certain things, right? And finally, nowadays, whenever you design, you want it to be optimally designed. When I walk, my entire thing is very naturally optimized. If you want to make a humanoid walk, deciding on how should I move, okay, what should be my next step so that I use least amount of energy, at the same time maximize my performance, have my stability, everything, is a very, very complicated problem. So easier way is somebody has solved the problem, nature has solved the problem, try to copy something from that. But we have actually solved some other problems, like we have wheel. None of our actuators are rotary. Even if I have a rotary motion, what is actuation actually? This motion, this joint looks like your, in robotics we call it revolute joint, right? This joint is revolute. But do I have a rotary motor here? Actuation is linear, right? So in nature, there are certain things but which is difficult to copy, but we have, I don't dare to say, but probably we can say we have a better version in terms of wheel and rotary things. So we will use them, okay? That is where the final robot may not look close to any of your natural either creature or element or things like that. In fact, Murphy defines is an artificial creature. Even the artificial intelligence idea, what is artificial intelligence? Why it is artificial? Because intelligence belongs to nature, right? You artificially try to evoke that. Machines are never intelligent, okay? What is artificial intelligence? In a given set of condition, if machine behaves similar to how I behave, you call it machine intelligent. But that is not intelligence. That is only copying the input-output behavior. Okay. So manipulator basically comes from the word. It's also called robotic arm because it is actually only the arm portion. Why arm? Because you perform all tasks by typically your hand, arm, right? And in industry, what is maximum used. Probably when you have to do, if a person, you have an employee who is actually doing assembly operation, will he have to move? Typically no, right? So that is why his arm is sufficient. So that is why you have a RAM. So when you have working with two arms, that is what I think you are talking about tomorrow, right? There is a collaboration between, for me it is my own two hands, arms. For robotics, this is a different robot, this is a different robots. So when I am actually trying to do something, with one hand something, another hand something else, I am trying to open a bottle, there has to be coordination between them, right? So this, and second thing is it's a machine. What is a machine? Mechanical engineers, any mechanical engineers here? Okay, so what is a machine? Definition of machine. It is a combination. What is the difference between, what is a mechanism? Not any assembly. Even this table is assembly of part. Is it a mechanism? It has to have relative motion. Motion is important. What is the difference between mechanism and a machine? Oh, sorry.
So machine it will be using for some particular task or useful.
To do any task. So task is actually computer science terminology. So let us get the mechanical engineering terminology. You perform work. Do work. Okay. To do work, what is required? One is motion. This is physics, not see what is all engineerings are basically physics, maths, and I don't deal with chemistry, so there are other things. And nowadays biology also comes into picture. So what is work? Motion and this anybody can answer. What is the work in physics? In context of course, it's a form. No thermodynamic definition. It's a form of energy. Yes.
Manipulation of something.
No, not that. What is work? Thermodynamics or physics? Force into displacement. So there has to be force. In mechanisms, there is no force, there is only displacement. That is where kinematics comes into picture. Mechanisms, you don't worry about their actual strength. You can have sticks, right? What is the difference between a mechanism and machine? Machine has to perform some work. If it has to perform work, it is so-called mechanical work. Work is that physics definition of work. Okay? So if it is work, it has to apply certain forces and move. If something doesn't move, then that is not a robot. So now, because of computer science perspective, even an intelligent piece of program is called robot or bot, right? Your CAPTCHA, what it does? Whenever you want to do something, it will ask for CAPTCHA. Are you human or machine? All right. Hey, we will not ask a machine to do that, right? Instead of that, we will have an agent, which is a soft piece of software. Okay. So why it is still called a robot? Strict definition, it's not a robot because robot is a machine. So it has to have a physical body, and that body has to have relative motion either within or move as a whole. Right, your typical manipulator is the base doesn't move, only the end effector moves, and using the end effector you do certain manipulation, right? If it is humanoid, then entire body moves. If it is a mobile robot, entire body moves. You can have put a manipulator arm on top of a mobile robot or even UAVs, okay? Then this combination comes, right? So where were we? What was, why did I ask this question? The question before?
It's called a robot.
Yeah, why that software piece is still called robot? This leads to artificial intelligence. And this question, again, answer is same thing that I gave. Why robot? What is the fundamental aspect in robot? Because it behaves like a human being. You are getting confused whether a piece of program is doing this job, answering you. In an interview also you can do that, right? Nowadays, in fact, Google themselves, who are creators of AI, they are worried about when they recruit, people use their own AI to answer and crack their test, and they do that job, right? You do not know whether a human is doing or a machine is doing. When you have that confusion, that is why there is a relation between human beings, biological things. That is why even such programs are called bots in computer science technology, but they are not formal definition. Formal definitions somebody told it's a mechatronic device, to be precise. Nowadays, it need not have electronics. It need not have your software code. A robot can have pure mechanical logic. But practically now we don't have that. You need not have motors. You can have pneumatics and hydraulics to drive that. You could have some mechanical logic. Okay, there are mechanical computers, if you are aware of, again through mechanisms, right? So you can do that in principle, but practically now all robots have to be mechatronic devices. Okay, so the mechanical portion actually takes care of relative motion and supporting the load both. If it is only mechanism, it need not support load. So if I am actually designing this mechanism, I should be able to lift this. Moment I lift this, there are forces here, right? And if I move that, I do work. I hope even non-mechanical engineers are fine with this, right? That is your physics. If you displace a force by some distance, that is work done. That is what is a mechanical energy, right? So the electrical energies in the motors are converted into mechanical energy in terms of work. Now, all these things is basically trying to say, in word we have motion, right? Right? So the motion is very important. If it is a manipulator, then I am worried about motion of the end effector. Okay? If it is a mobile robot, I am worried about moving the robot as a whole. Okay? Since it is a very small group, I know you are all my colleagues, peers. So if somebody is dozing, I will wake up. So don't feel bad. Okay? I'll help you be alert. Okay. So basically, you have to move in a certain fashion. How do you move? When I have to go from here to there, if I from here I go and after my talk is over, from here I have to go and sit there. How do I do that? I need to have a plan in my mind, right? How am I going about doing that, right? So I should know that I will turn like this, I'll go like this. Okay, there is an obstacle here. There is an obstacle here, that comes later. Okay, then I have to decide on how I put my leg. Or if I have to take this from here, put it in my hand is here. I have to go here and pick it. Way we do is different. Okay, that's a different thing. But you want a robot to do this. If you want a robot to that, many of you have told it is programmable. That is very important component. What do you program? Unless you don't know what to do, you cannot program. Right? So how a washing machine works? Why a washing machine is automatic? There is a semi-automatic and fully automatic washing machine. What is the difference? All of you might know what these two are different, right? So the semi-automatic is not called manual. It is still called automatic, but we call it semi-automatic. Whereas other things are called fully automatic. What is the difference? There is after one operation, there is a human intervention. But within that operation, it is automatic. What is automatic there? Have you observed what, once you put, have you very curiously looked at what it does? Because once we get used to that, we don't bother. When you have your washing machine for first time, you know, when it spins, it looks, okay, current generation kids may not have that excitement because it's a part of their life. So we had transitioned, so we know that. So what it does, what is automatic in that? Not exactly. That requires programming. Okay.
There are several steps.
This is important, but in slightly different context.
How much? What is
That nowadays we call it smartness or something like. Let us say everything is set. You are switched on. After that, what happens? There are several sequences. This is automation in industry automation or whatever it is. There are several sequences of operation, right? First, it has to put the water, release the water, open that. For how long? That is what is programming. Open the valve, okay? After 10 seconds or whatever it is, or after filling. It need not be feedback controlled, it can be open loop control, right? You let us assume it is open loop control. It is time-based, relay-based automation kind of thing. You open the valve for 30 seconds, right? And then don't do anything for say few seconds. I don't know how it works. I'm just saying for sake of this thing. Then you start spinning at certain speed. Okay, after you start spinning at certain speed, you drain the water. All these sequences of operations, who tells that? There is a piece of program running that, right? The program says when you have to start something, this is your current day generation program, whatever you write. So those kind of things. So there are different operations, how long each operation has to happen, and how do you switch from one, at the end it will drain all the water and then start spinning very fast because centrifugal forces will throw away the water, right? So it will almost dry it. If you have a true dryer, maybe it will use change the program that way. But I think the true, I had a very old washing machine when I was doing postdoc in US, very old one. It had everything automatic, so including the complete drying, hot drying. In India, what we mostly get is, it is more like you squeezing that much drying. If you want to complete drying, you have to put it in a, typically, most of the times, I don't say that such machines are not there, but they are not popular. This sequence of operation is what is, it is pre-decided, okay? So this is planning, right? So if I have to go from here to there, from here to there, I will say this many steps I have to come, simple, stop here, then change the program to getting down. Okay, I don't want to get down here. Okay, get down and then walk straight for some time. Then you change the direction. Maybe I have to change direction. All these things are sequences of my motion, right? Now the task we have is only motion in this particular topic. So I have to move. If I have to move, there are sequences of motion. How long I have to keep certain motion. If you want to program this, I need to know all these bits and pieces, right? That is what is planning. The word planning is actually computer science domain. Okay, fine. So this part is actually from the perspective of manipulator, but same thing applies to a this thing also, a mobile robot also. Okay, I have actually told all those things. I'm strictly not going by my slides. Okay. Any doubts till now? This is only motivation for why we are doing. Okay. What is compared? There are different terminology. This is very important because we actually get confused with a lot of things. What is motion? Motion actually is talking about change of position on the orientation with respect to time. Orientation is also important. Motion planning problem is not just come after the robotics. It was even before. There was some piano moving problem. If you have to move this table from here to somewhere else, what you have to do? Suppose I have to, okay, that foot, let us say this is a small, some big planar stuff, some big screen is there with me. I want to move it out of this hall to take it out of the door. What will you do? I pick up and directly go? It will not go outside. Okay, I pick up from here to here I have sufficient place. I can pick up it like this, right? Suppose assume that this is something which I have to move. How do I move from here to, so here to there I can move like this. Then after that, if I move like that, what happens? It will fall. So I have to move like this, right? Now what I have changed? Position and orientation. Now suppose, let us assume, we will simplify the problem, door is open. Okay, opening door is not problem of mine. So I cannot go like this, right? Maybe I cannot also go like this because I am too tall. Then have you moved? You would have experienced this when you are moving stuff, furnitures, changing house, or moving one big cot from one room to, changing the bedroom. You would have done that. That is a motion planning problem. When we do, we use a different kind of technique. Okay. But if a machine has to do that, you have to tell it every steps. If you don't tell it to turn, what it will do? It will straight away go and hit it, right? Either you have to tell it, that is planning. When it becomes so-called intelligent or autonomous, see, automatic is, what is automatic? It will tell exactly whatever I do. Okay, if I ask it to go like this and there is a big well, it will go and fall into that because I have not told anything else. It will just do that. A dumb person also will not do that. But a robot, typically an automatic robot, does that. If I say you take this, do like this, right? It will blindly do that, whether it is possible or not. What is the difference between autonomous and automatic? Because these things indirectly come in all these things. So the first part is typically automatic only, not autonomous. The second part I am talking about, he is talking about, I think he will also bring in that. And tomorrow, Dr. Soumya, she is my PhD student. Okay, she will actually talk about same thing. We talk to each other, but she will talk about implementational issue, practical issues. I will give you an idea about that. Basically, what is the idea behind it? I will show you some math and some details. I will not only talk in English, okay, but I want to be sure that you understand what is going on, because there is a heterogeneous group, right? So you come from different backgrounds, so you should understand basically what the problem is. Then the solution becomes easier. That is the idea, right? So that is automatic. What is autonomous? So how do I solve the problem? So he will tell me, you go from here to that room and get me a water. That's all is the instruction. Will he tell me you walk 10 steps like this? Your Google Maps says that. Okay, that is why some people follow Google Map blindly and fall into river, because there was no bridge and Google doesn't know there is no bridge, and the person driving doesn't use his brain because he has more faith in his Google Map than his own brain. So he will drive fast and fall into the bridge, and that's unfortunate, though I am saying it in a funny way. And even Apple Maps people have sued, right? So it takes you to jungle and there is no way, and I have experienced it, okay. Not in jungle, even in the cities, it will take you to the thing, then there is no further road. It has happened, I know this area very well. I drive from Bangalore to Mysore and I wanted to take a shortcut. It took me somewhere and in a residential area after there is no road. I know I am very close to Mysore road topologically, but I don't know the graph network. So I became helpless. So this happens, right? What I will do, he will not give me that complete instruction. I will decide, I will see, when I am walking from here to here, it's a straightforward problem, but it is not straightforward problem. I know sometimes what happens, I am talking to you, I will do like this, right? That is because I am not looking at it. So this is close to your, in control, you have open loop and closed loop control. This is something like that. You sense the environment. I have the slides later, I will talk about that. So you do it in a different way, the planning, okay? Both of them are planning, okay? So this is basically what is a motion, okay? So in the context of manipulator, what is the motion? If I am using this, see, if I have to write on the board, do you have a, okay, I will not write, don't worry. So this is a pen. I have to write on the board. I have to make a circle on the board. What I have to do? I have to orient my pen like this, right? If I orient my pen like this and move it on the circle, will I be able to write? Even if I do like this, it will not write like this. This is good, but typically you do like this. For example, 3D printing, you are giving it to move around that, right? But the orientation is also important. The position and orientation as a function of not exactly time, it changes with time. It's not as a function of time, right? If I do it fast, I will do it fast. If I am writing A, I can write it slow. If I am writing, say, V, if I am writing V, I can do like this, or I can do like this. Both of them have same motion, right? So the motion includes both position and orientation typically. A path is only position. Okay, so it's a sub-problem. So most of the times we say motion planning, we do only path planning. When it is sufficient, if I have a circular, if I have a car, I will have to do motion planning. If I have a circular kind of robot, does it matter whether it is moving like this or like this? It could have a differential wheel so that even direction changing is not an issue, right? So only the heading direction is important. My heading direction will always be in the direction of me moving. If I have to go like this and from here I have to turn, I'm not basically turning because of my required orientation. I'm turning because I have to go in that direction. So the path related to motion, path actually only talks about sequence of positions. Motion talks about sequence of position and orientation both. Typically we say motion planning in general, but the most of the times what we will be solving in context of mobile robotics is path. Okay, but it depends on the mechanism of the mobile robot. If you are doing, for example, a quadcopter, motion path planning will be sufficient. If you are talking about fixed wing, path planning will not be sufficient because you have to bring in orientation because it can move only in this direction. Whereas quadcopter can move like this, move like this, move like this, move like this, move like this. It need not turn and move. Okay. Similarly, a car, you actually require a motion planning. Okay. But most of the times we will talk about the sub problem which is called path planning. We will not worry about this most of the times, but it in certain practical scenario that is required. Okay. What is trajectory? All of you have studied projectile trajectory in physics in before coming to engineering, right? What was that trajectory? Trajectory of the bullet fired. No, that was the starting thing. Do you remember what did trajectory mean there? It need not bring in velocity because once position is with respect to time, velocity automatically comes. It is basically either your path or motion along with the time stamp. Okay. Why that is required? Typically for robot motion planning, you decouple velocity and path. If I have to move from here to there, if you want to move fast, increase the speed. But I only specify what is the path, right? I need not specify what time you should be here, what time you should be here. It is up to you. Which speed you want to move from here. If I want to make a quadcopter, go from here to here, right? There are a lot of obstacles. It has to move through the free space. So I will give it a safe path through which it has to move. What speed it moves, it's up to us. Does it make any difference in that problem? Same path you can follow if you want to go at 10 kilometer per hour or 20 kilometer per hour. For example, if you have to come to from Bangalore to Mysore, the navigation will give you only the path, right? So subtle orientation is part of it. That is not explicitly mentioned, right? So it is only path planning problem. It is not trajectory generation. If it is a missile, it is a trajectory generation. Why? The time step is important. You have to keep waking up him if he doesn't feel uncomfortable. Okay. Fine. Why is trajectory more important in manipulator kind of?
Shortest possible path.
That is path planning problem. That way we might talk about that today. In case of robot, if I have to move something from some place to if I have to move the end effector, you give me an example where time is crucial. I give you an example. If I have to write on the board, what was important is only the motion of the pen. It's actually motion planning problem. But if you are not changing orientation in between, we need not worry about the orientation part, solve it separately and then only solve path planning. Because path planning is the easiest problem. You have to worry about sequence of only the position. In case of mobile robot, it is position of robot as a whole. What is position? What is the position of this fellow? This is a pen. This is a pen. If I say position, this is a rigid body. I want to go back. Okay.
Position of that object in space.
But object, what object?
Whatever object you are considering.
But what is the position of entire object?
X, Y, Z.
Of what?
The tip of the pen.
Respect to
Tip of the pen. Position is only for a point, not for a rigid body. Right? There are, how many points are there in this rigid body? Assuming it is rigid body, there is no rigid body in reality. For practical purpose, it doesn't bend when I am performing. If I am using, some very slender kind of material and while writing it bends, we will assume it to be flexible. This fellow will not bend from practical perspective. It will actually bend, which we cannot realize. Well, that's a different thing. So practical purpose, this is a rigid body. Everybody understands that? What is a rigid body? At least mechanical engineers?
When we apply force which do not deform.
From this perspective, position and orientation, there are infinite number of points. What happens to between 2 points? Relative distance between any 2 points within the rigid body will not change. But whereas flexible body, it will change. So that is why whenever possible, we will assume something to be rigid body, unless that it cannot be further neglected. Okay, say rigid body, what do I mean by position? I have to talk about position of a representative point in the rigid body, right? If I'm throwing a ball, what do you think is the point that I'm tracing? Trajectory problem. You are interested in cricket, I will decide, I'm not a cricketer. I'm not anti-fan, but I see cricket, but I'm not a fanatic of cricket, okay. But most of people are, right? So you talk about a bowling thing, okay. You might, from robotics perspective, you might be interested in making a robot which actually bowls and helps somebody train for batting, okay. You can make it learn how a expert. And now for timing, assume that you cannot learn anything. You have to do everything yourself. Only then this is required. So unfortunately, if you can do anything with a black box called neural network. You just copy how he is doing and I can do it. You know that, right? You can copy whatever I make a speech and then my voice, and you can make whatever you want. You need not know how I do that. You just blindly copy. That is like our students copying from somebody else. It's nothing more than that. So learning is basically that. I'm not saying it's not required, but that is not everything. So please be aware that these deep learning, machine learning and everything, they have their own limits, okay. What is learning? Basically, you are just copying, but you are not able to copy. If you want to do that, what you have to do? What decides the bowl's trajectory? Suppose you have to make a robot, you have a gripper like this, it will hold a ball, okay, and you have mechanism to release at right moment. You can loosen the grip, that's all. But you have to rotate the wrist, right? You have observed people bowling. What are the two things? They will run to get the momentum, okay. This is where the mechanics is important. They will rotate their hand because this also adds the centrifugal this thing, and there is a momentum at the time of release, okay. So that is what will be its initial conditions, right? Once you leave it at the initial condition, then how do people spin? Anybody observed?
Rotate the ball.
They rotate the wrist. You cannot rotate the ball, I can only rotate the wrist. Okay, from your robotics perspective, your robot this fellow should rotate wrist. There's a trajectory planning problem for my robot, right? So I have to say that you have to go like this. Robot probably need not go there because it has got powerful motor. From here to here, it can accelerate so much that a human being will get by accelerating this much. So that is possible. So you just do like this and release. Now there is a rotation and this thing happening. But if you want to track the ball, what do you track? Position of the ball. That typically CG of it, right? So what is if this is an end effector, a pen, a writing robot, what is the point you track? This position is this. What is the orientation? Orientation refers to the rigid body as a whole. So if it is rigid body as a whole, if it is flexible body, again it is more complicated. Each point you will have a different frames of reference. Okay. So if I have to write here, if I write faster or slower, it may not make much difference. But if I write too fast, what happens? There is no time for this fellow to deposit and you cannot write. If you write too slow, what happens? Maybe it may deposit something more. So you have to decide on the speed. Now forget about that. If you have to do welding, what will you do?
It's the speed.
The speed is very crucial. If you go slow, what happens?
More deposition.
More deposition. Or if you do gas welding, what happens? If you do slow, instead of welding, you will cut it, right? It will become gas cutting, right? So the speed is part of your task. Whereas in mobile robot path planning, speed may not be part of your task. If you are talking about missile guidance, speed is part of your task. So if speed is not part of your this thing, you only worry about path. Where was the path? Path. Okay. The real problem you want to solve is motion, but typically most of the times you will solve. In context of robot, this is also a motion planning problem, but along with the motion, I am worried about the timestamp. That is why that it becomes a trajectory. That is the difference. Okay. Okay, so this is typically so-called computer science problem. I am not a computer scientist. I work on that problem. Okay, and I should have a picture. Let me see that if that is there. Unfortunately, do you have access to a board if I can write? In computer science, what is planning is actually part of a bigger picture called there is, you sense the environment, and then plan your action and act on your plan. So this plan, sense, plan, act is the paradigm used in computer science. So the plan is that part. Okay, this is basically definition of an autonomous agent. An autonomous agent, for example, I have to go from here to here. Okay, so let me say I have to, okay, I have to go from here to here. What all I can do? I sense my environment, no problem. I know my goal is there. I make a plan. If my goal is there, I have planned my path. What is my path? By default straight line. I move like this. Now I keep sensing. Here I sense there is some obstacle. What can I do? Either I can go like this, that I will talk about, or manipulate the environment, go there. All right? What I am doing, this is a classical computer science problem. So I sense the environment. I am called an agent. This is the environment. Okay? I can act on the environment and manipulate the environment. I am capable of doing that. But most of the times, machines do not do. Because for them, machines to take a decision whether this is movable or not, that is one thing. Whether I am permitted to move it or not, I do not know, right? What is the implication of moving? So we will also get confused if you are in a new place, you do not know, maybe that setup I should not disturb, right? So that decision becomes very important. Okay, this paradigm, the people, are there any computer science? Yes. So you are aware of this, right? So you have sense. This is called an autonomous agent. Okay, since this basically comes from my textbook and I have not put together anything, I have just took one chapter and putting things. So these things are there in the first chapter. Okay, so this is the paradigm under which that planning happens. Okay, so planning basically you need to have use lot of computations, lot of intelligence and things like that. That is why it becomes part of, whenever you word planning, remember that is part of AI. Planning is part of AI. Okay. So original problem I have told you, I think I used this word, right? Piano movers problem. It was called that. Okay. Path planning is restricted only to obtain only the path. We don't worry about motion, because most of the times for robots nowadays that are coming, because I am working on a DRDO project where we are not doing that, but when we interact with the DRDO scientists, they bring in the problem where you might be moving with a large humanoid. Okay, so then see, when we are working only with a mobile robot, okay, let us not worry about steps, because normal mobile robots cannot climb. So I worry about a problem where there is a large area. If something like this within this domain, if I have a mobile robot, it will not be able to go like this. It will have to go like this. But robot as a whole can move. So the orientation is not a big issue, right? But if you have to move around in a forest, or you want to go to old houses with this thing, you will have to move like this. Sometimes you may have to do like this and move, right? So you cannot actually, even relax and move. Then things become much more complicated motion planning problem. Okay, so the motion planning problem is still very important, but the middle, there are a lot of problems where orientation may not make much difference, so you solve the path planning problem. Okay, and they are not, they are coupled problem, but sometimes you can get a simpler solution where you can actually solve path planning problem separately. And suppose I have to now go through the narrow path, worry about orientation planning at that point of time. So I will not talk about motion planning, though my title talks about motion planning. And I think when Soumya talks tomorrow, she will also get into this, because these are now advanced kind of stuff which people will not touch unless it is really required. So practical purpose, there are two things which we are talking about. One is path planning, one is trajectory generation. Okay, fine. Okay, these are finally optimization paths. Somebody mentioned that, right? Shortest path is what? See, if I have to go from here to there, it's a straight line. But if you want to technically solve, you have to solve an optimization problem, right? And sometimes, you know, I told you about this, right? This is called gate synthesis, right? So if you want to make a humanoid and humanoid to walk, okay, so you have to take care of lot of things. One is simple, next step should be kept here, okay. One is high level planning, that if I have to move from here to there. One is high level problem, you give me a path. So if I have to move from here to here, what I have to do? Wheel can just go. But if I have to move, what I have to do? I have to give, this becomes my manipulator kind of robot, right? I have to give the joint trajectory. This is again now becomes trajectory problem. Okay, where do I keep my next step? Whether I keep it like this, okay, what I do, and I have to take care of what? My stability. Okay, there is something called, I'm not getting the word, stability polygon. Okay, so if I keep my leg here, I'll fall, right? Have to, when I lift my leg or I keep like this, when I keep like this, I should keep such a way that my TG falls under this rectangle formed by a polygon formed by my foot. You have to worry about that, okay? And then you might have observed, moment you have some pain somewhere, okay? Whether because semi-permanent like arthritis or some tiredness, whatever it is, have you observed your gait changes? Way you walk changes, you limp. Why do you limp? Your brain solves an optimization problem. If your this muscle is paining, it wants to give it lesser load. It will try to, whether it does it perfectly or not is different, because typically this temporary change, I think our brain doesn't, if you have observed better example, this particularly dogs, you would have seen a lot of dogs with one leg broken or one leg not functional. They'll still walk how? They re-optimize, they rewire everything. There's a lot of optimization in terms of how much muscular energy I spend, how much I spend in this muscle, this muscle, this muscle, this muscle, because each muscle has got a different power, so power capacities. Okay, based on that you do a lot of this planning. Okay, so it is basically the shortest path is very simple, right? But it is an optimization problem. Since we know the solution, we don't solve the problem. We directly get the solution. Okay. This is one very important thing from perspective of motion planning. Trajectory generation typically is an offline path. Okay. Since I have this definition, that is where I don't like. If I come physically here, people call it offline, because it is opposite of me sitting in Kanpur or Madras and doing online. Because online has become, what is online in that context? It is online in the sense it is live via internet. It is basically remote, it is not online. Okay. This is face to face. Both, it is online because it is live. What is offline? If I am sitting in Madras, I can give this talk online and offline. What is online? I sit there now and talk now. It is live. Okay. I would have recorded yesterday. I played it today. It is offline. That is online and offline. Not, I mean, currently after COVID, this word offline is something which is misused. What is offline in this context? If I have a robot, okay, I want robot to go from here to here. Okay, suppose I want robot go from here to here. I know the room. I know there is this chair here. I know there is a table here. Okay, let us assume that robot will not be able to go under that. Let us assume it is a solid obstacle. What is offline path planning? I actually do something, whatever I do, doesn't matter. Find out some best path. It need not always be shortest path, because for example, in case of UAV, if you have to do the path, the shortest geometric path may not be best path for UAV because it cannot turn instantaneously. Okay, so that depends on that. So I decide on the path and then put the program, write it as a program. This fellow is dumb and automatic. He will just follow the path like this. Okay, that's done. That is offline. What is online? You don't tell anything. You tell the robot you go from here to here. There's a planner sitting inside, or maybe it is connected to a laptop. That also is fine. It might be doing cloud computing, that is fine, but it is doing computation on the spot. What I do, I sit here, I decide on a path that I have to go. I know that my next point where I have to go is free, I go. Then again see, next point is free, I go. Here I see there is an obstacle. Now, if you want to make online path planning, what is the capability you have for the robot? You can have a very simple robot. If you want to implement offline path planning, do you need sensors for the robot? No. See, this is the robot. I have told the robot you have to go like this, go like this, go like this, and go like this. What robot has to do? Only that. It cannot do anything if there is no road. Right? That is strict offline path planning. It doesn't require anything. You can have a very simple robot, right? Now, if you want a robot to implement an online planning, this planning, action and sensing, I told you, they are happening together. What happened in earlier this thing? There is no sensing because sensing is done at the planning level. Plan is given. What the robot has to do? Only act on the plan. If it cannot act on the plan, what does it does? It cannot do anything, right? Now, what is online path planning? What does your robot have now? It should have sense, because it should sense the environment, right? Then it should be able to plan. What is planning? It needs to have intelligence. Okay, so it is taking its own decision what to do. What is the decision? I come here, I see this thing here, right? You have to take a decision what you have to do, because you know that this thing doesn't work. So what is the decision it could take? Change the direction like this or like this, right? So maybe let us assume by default it will always move to the right. Okay, that is not that obvious. Okay, so it should be able to take decision. If somebody has to take decision, he has to be intelligent, right? So if you want to take decision, you need two faculties. One is intelligence, another is authority, right? So earlier this college was under Mysore University, JCE, right? It was under Mysore University. Okay, now let us not consider it is JSS University, but most of the university institutions now are autonomous. Why they are not autonomous? What is the meaning of autonomous? They can take their own decision. So the authority is given to take your decision. But there is a process involved. They will not blindly give you authority. What is that process involved? They will know that you have sufficient resources and ability to take decision. In this context, what is ability to take a decision? If you have a travel agent Okay, you just tell him that I have to go to this thing, these are my constraints. Don't bug him too much. Only if he is intelligent enough, he has got a lot of expertise, you will give him that authority, right? If he is a person like me, he says this ticket is not available, he'll ask you what I have to do. Then you will not give him because he doesn't have that capability to take a decision. To take a decision, you require one thing is your own capability, that is intelligence. Second is authority to take a decision. So first of all, I have given this robot, it has got capacity to, ability to replan. Moment there is an obstacle, it knows it, you know that it can do something. What is the simplest thing it can do? Stop. Don't hit. Stop. Even that is good, right? Stop and report is also sometimes fine. This in any algorithm, what is extremely important, this is computer science perspective, any algorithm, the algorithm should be able to tell you, because you never know the situation, right? You should be able to, sometimes in human beings we don't accept that, that is our behavioral mistake. So you tell somebody to do some task, and if he sincerely says, no, I could not do that, you should appreciate him, right? Instead of him doing something, some blunder, right? So this fellow, if it is says, I give it a problem to solve, actually it doesn't solve. My algorithm sitting inside that is solving. So it is not dumb, I am dumb, the person who programmed it, right? So if any algorithm, it cannot give you a solution, it should tell you, I cannot find solution. It should not give you wrong solution, or should not get stuck, or should not get into infinite loops. If you apply somewhere for faculty position, okay, ideally you should get an interview call, you should get selected, everything. But what happens if you are not getting a call at all, whether you are selected or not, whether your application has gone to dustbin or not? The system should give you back the status. If I am not able to recruit somebody, I should tell him, no, I am not going to recruit somebody. Okay, so that is one important thing. So that is what is online path planning. That we will try to touch up on that, and tomorrow I think I will discuss with Somi anyway in the evening, so she will talk about it. I think you will also have a lot of these things coming up tomorrow. I suppose that. Okay, so if the entire environment is known perfectly, okay, then probably you don't want to do online path planning. Offline is good. Tell me why.
Change of position of environment.
Offline, what happens is, I know entire environment.
Not damages its own parts.
That is a safety. Let us assume that it has got that much ability that suppose I gave it an offline path and that path is not feasible, it should report and stop. Let us assume that much it does. Okay. Now if you know entire environment, which one is good according to you, offline or online? Offline. Why? Two reasons. One is, computation indirectly comes. Okay. You know entire path. You can give really the best path. Right? When I'm moving like this, for example, I'm here. Okay. Let us assume this is very long there. Okay. I am come here. I do not know. I cannot see beyond this point and this point. I don't know how long this is there, how long that is there. Okay, probably I will move like this, and then I may have to keep moving like this. Whereas if I moved from here, maybe I would have got the path easily. In an online, it is something like you can only see this much, right? And if you imagine if there is an UAV flying above, which is assisting me, then I can myself, the robot sitting here can do entire planning offline. It need not be coming from somewhere else. So that is, first of all, you can get the best or optimal path. Okay. And of course, somebody told online you have to do what you have to do. Each and every step you have to sense. Okay. You do not realize. Once you have to sense, what happens? You get the signal. That signal has to be processed. It has to be interpreted. These things are not easy, particularly if you know of Kalman filter and things like that. Sensory informations are not perfect. You may want to go through Kalman filter. Again, that is a big process. Okay, and then at the end of the day, your sensor may be giving wrong results also. So you spend so much of computation, so much of time. So each portion I have to sense, I have to plan. This takes time also, right? So I have to kind of stop in between. It's less probable that I can continuously move. Now if your computation is very fast, time may not be issue. But you cannot afford to have very fast computation, how much ever processors are improving, speed is improving, because you want to pack everything. There are new challenges, there are new problems to be solved. It's not only motion I'm solving, right? The robots are not just for moving. Remember that. What is a robot? Somebody told it has to perform a task. It is multifunctional. It has to do a lot of things. If it is only moving, then there is no issue. For example, if you have an UAV flying, what I want the UAV to from robotics perspective, nowadays what do students do is they just move around, because that is most difficult problem. Okay, then I have to sense something. Maybe I'm doing, he mentioned I work on search and rescue kind of thing. I only work on the theoretical aspect of it. So it has to go get the images or many other sensor data, find out if there is any person who is requiring an assistant now, then alert the team. It has to do some other tasks also. The computation is required for everything. So if you eat up all the computation power only for motion generation, it becomes difficult. Okay. So there are offline or online this thing. So remember this, online is fancy. I am fan of online path planning. I don't like offline because I have a lot of opportunity in generating algorithm. It looks fancy. But whenever it is not required, don't use any fancy stuff. If something doesn't require automatic, don't do automatic. Do with the simple thing. That is always important. Okay. Okay, so I have talked about all those things. So I think there was one picture here. So I gave you exact same thing from this perspective. Okay, if you have to go from here to here. Now imagine, for example, this fellow is very long here. Okay, or even in this case, this is good. Okay. So now if it is offline, I know this part is smaller than this path, right? There are two possibilities when I encounter this. I can go like this. Okay, even after going like this, I do not know what time I have to turn. On pictures, these things look very small. You have to think that your robot can see only just in front of it, doesn't know any information. Then the algorithm is very challenging. When I give you the complete picture, you think this is child's this thing. This is not easy to do. Okay, this is basically called a bug algorithm. In fact, this is not an optimal thing. Optimal thing will be from here you straight go. That is called tangent bug. Okay, and in fact this is not optimal, because if you have known this fellow is there here, what you would have done? What is the best path? Tell me now. You know complete thing. Shortest path. Not don't worry about anything else. A tangent to here and tangent to here. But I have seen this fellow only after coming very close to it. So now I have to replan. Okay. So I like this kind of problems because I see geometry in that. Geometry and common sense. I am not an algorithmic person, but I work on these things from that perspective. Okay. So this was the initially path. So from here, I will think that I will go like this, but moment I realize that, I will go like this. It is not guaranteed. I might have taken a decision to turn like this. Sometimes it may happen that there is no path at all here. Okay, this fellow can be like this, right? Because from here, do I see entire obstacle? I see only part of it. Just in front of me, there is an obstacle, nothing more than. I don't know how big, nothing, right? So this is pure online where I do not know anything about the environment. Okay, there is no mapping done. I will talk about that later. Okay, so this is what I told you. So here actually robot senses the environment. In this context, what is sense, plan, act, bumps? Senses the environment to know the presence of obstacle, computer science perspective. Plans to turn, okay, in tangential direction. And then acts, that is basically moves on that direction. Sometimes action could be moving the obstacle if it is possible. Typically, in a standard path planning problem, you will assume that obstacles are not movable. But in reality, I mean, I told you that scientist I was talking about, he says if I can move something, if I can get a path, I'll move. But to know whether that is movable or not is not easy. Even sometimes human beings, if you see something new, we do not know whether it is fixed on the ground, whether it is movable, or sometimes you may not know, it could be bomb also, right? I mean, there are a lot of issues, right? So, remember, taking decision is not easy. So, you don't think robot is you, okay? So, what you should do, if robot is you, what robot should do, then you have to go so much deep of what all analysis you do in mind, or put a black box called neural network, you move around your and make your robot learn. Nowadays, that is what is happening. So you do not get that, have that enjoyment of deciding on, for example, walking also can be done that way. I need not worry about anything about physics or mechanics or any of those things. I will observe me walking and make my robot just copy that. It is not blind copy, it will actually what neural networks do is something called function approximation. You do not know the function, this thing, but you know for certain inputs it will give you certain outputs, right? Now if you actually make that function approximation, because neural network is nothing but it's a bunch of mathematical computations that are happening. Slightly much more complicated, lot of networks which are computing, each component is doing some very simple computation, but it can actually do this nonlinear function approximation. That is why it works. Okay, so we have time till 12, right? Or is there a break? Okay. 11:30 we will take a break. Okay, this trajectory planning is something more useful. I don't want to split up, but more useful for people who are working on manipulator. Okay, so I'll change the gear slightly. I will briefly talk about trajectory generation, certain techniques that are available there. Okay, what kind of math that anybody has done the trajectory generation in till now? No. Participants, any of your previous lectures have covered, or any future? Can you give me this thing? If somebody is doing that, I can very briefly cover that. Yeah, there are a lot of talks which have titled autonomous robotics. So what is being covered is, he told me he's talking about collaborative robotics. So I'm not touching upon your this thing. Okay. Okay, so this formal stuff is not happening. So this is a very important problem because manipulation is coming back. Even if you're not interested in industrial manipulators, okay, so more of AI level of robotics if you are interested, such as mobile robotics. Now we talk about mobile robot, on top of it there is a manipulator sitting, okay, or you have a UAVs where a manipulator is hanging, and then you have to still do these things, okay, in a different level. So as I mentioned here, typically in robotics, in this thing what happens is, either you're not too worried about path, you're only worried about initial and final point. Okay, for example, if I have to pick this fellow from, I take pen from here and keep it here. What I have to do? I have to go here. Picking is not part of trajectory generation, okay. Then from here I have to come here. How do I come? I can come like this, I can come like this, I can come like this. Do you bother? No. There should be some optimization, that is a different thing, okay. And remember, moving in a straight, if I have to go from here to here, moving in a straight line is not always optimal. Because how much my muscles are not moving in a straight line. These fellows are moving. For them, individual trajectory might be more longer, or they might take more energy. Okay, that is why we have number of degrees of freedom are much more than what is required. That is 6, right? Your hand itself has got more than 6 degrees of freedom. So 1, 2, 3 here, 1, 2 here, then there are here, then we have fingers, everything, right? So you have more degrees of freedom. So we consider first 2 kinds of problems, where one is point to point, I don't bother what is in between, but what is in between? If I have to take this fellow, if I am coming from here to pick this fellow, what is the requirement here? What is the initial speed? 0, right? Position is given. Here position is given. Can I come with high speed? What happens? You don't pick up, you throw it, right? So when you come here, your speed should be low. Where else you think this problem is very interesting? Satellite, what is it called? Space station you have heard of, right? How space station is built? It is built there, right? So something there. When you build something, what you do? You add components to it and assemble, right? The assembly has to be done there. Same thing, similar thing. So I have one space station here, something has to go and attach to that. It is called docking. Okay, this fellow goes like this, what happens? Space station will go somewhere. That too in space, you don't know where it goes. So what should be the velocity here? 0. What should be its orientation here? Perfect. It should, if its velocity is 0 here, velocity is 0 here. So in between velocity has to be something, otherwise you will not move there, right? That trajectory becomes very important. Okay. So these, whatever I talk about here, have application somewhere else, but I am talking from this perspective. Okay. Okay. So now if I have to do welding, say, how do you specify the path? There is something called inverse kinematics and forward kinematics. So many of you are aware of that. This is a rigid body, the end effector, the tool that is operating in this space, physical space or workspace, right? What about these fellows? Robot? Does robot know XYZ, alpha, beta, gamma? This fellow knows theta 1, this fellow knows theta 2, this fellow knows theta 3, right? The robot knows where its position and orientation in its joint space. What is joint space? Theta 1, theta 2, theta 3, theta 4, so on. Say it is a 6 degree of freedom robot, theta 1 to theta 6. So robot knows that. But do you care for that? You don't. You want this XY should be 0, 0, 0, something like that, right? So this should be there. So this talking between the joint space of the robot to the physical space, it's called task space in the environment, is called kinematics, forward and inverse kinematics. Okay. So your actual trajectory are typically in the so-called not joint space, it's in the task space. Okay. So you have to decide what should the position and what should be the orientation. Okay. That's represent position and orientation of the tool. If position and orientation of the tool should be something, then I should have, understand this problem? Suppose you take this problem. If this has to be x, y and theta, then this should rotate by some theta 1, this should rotate by some theta 2, right? So the robot operates in theta 1, theta 2 space, but you are solving problems in x, y space of the tool. This transformation between these two is not linear, so I cannot get into that. Okay, that is what this kind of books, my book I told you, right, that, or Craig or many of these books talk about that. This is how you talk between these two spaces. Finally, robot moves its joints. Robot doesn't directly move this. If this has to be moved, this joint has to be moved by some amount, this joint has to be moved by. This has to move fast. Who is moving fast? This joint and this joint. Theta 1 dot, theta 2. This motor will rotate at higher RPM. This motor will run at higher RPM. As a user, you are interested in motion of this rigid body called end effector. As a robotist, I can control motion of joints. Remember, understand these two problems? Okay. This doesn't happen much in, this is there even in mobile robotics. Okay. But that connection is different compared to this. Okay. And in mobile robotics, we will somehow assume that is taken care of and only solve the problem in the actual space, task space. Okay. So what is typically given is where I am starting from, okay, and where I have to move. At t is equal to 0, I should be in x0, that is my current position. At t is equal to tf, I should reach this. This tf is important. I have to move in that time. I should not move earlier, I should not move later. That is given to you, okay. This is minimum thing that is given to you, fine. Now there are two schemes. What I can do is, I have to move, I have to take this from here and keep it here. What is given to me? x0 is this, x 5 second is this. What I do is, here I solve the inverse kinematics problem. I see what is my joint angles corresponding to this. Call it theta 0, okay, okay, and I solve my inverse kinematics problem here, and I see what is my theta zeros. I'll make the problem simple for you. I have to move from here to here. Okay, you can see my hands, right? The angular positions are changing. How did I move from here to here? By rotating this joint and rotating this joint. If I know theta 1 and theta 2 at this point, I call it theta 0. If at this point I call it theta 1 tf, theta 2 tf, okay. In between do you bother how it is moving? You don't bother. So let me solve the problem in theta domain, okay. So task space is directly solve the problem here, okay. So what I will do is, I will skip the, there are advantages in both and disadvantages in both. For example, if there is an obstacle in between, obstacle comes in the task space, not in the joint space, okay. So I will not know that. So if I have to go from here to here, I cannot go like this, I have to go like this, right. So this problem cannot be solved in joint space, I have to solve it in task space, fine. There is something called configuration space. This is very important. We always want to consider robot as a point, okay. So if I am this big, okay, if this, can you give me something bigger? I don't want to move myself. Okay, that is good. Okay. So this has to go from here to there, right? Now when it is going, can this go up till here? What is the point you are considering as a reference point? CG. Can CG go up to here? CG can go up to only here. So there is this much gap. How do I know I have to give that much gap? My path planning, if you see this figure, I did not consider size of robot. Robot could be this big, right? Robot cannot really go up to this point, right? So if this looked very easy for you, if the robot can become a point, then things become easy for you, right? So that is where this comes into picture. I should give you those. Thank you. Let me see if there is a figure. Yes, this will explain everything. This is actual mobile robot, okay? This is actual robot size. This black is actual physical obstacle, right? But the closest distance with collision, I cannot move beyond this, right? Right? Either throughout my planning, I have to consider size of my robot. It becomes difficult. So what I do is, I'll consider my size of robot is 0 point. Whenever there is an obstacle, I add the size of robot to it and expand the object. So this is called configuration space. In the configuration space, the obstacle becomes bigger, robot becomes a point. Then your problems become slightly easier to solve. Okay, but there is a problem. This is a very simple problem. Configuration space is, but the dimensionality is issue. For example, if you have 10 degrees of a manipulator, what is the dimension of physical space? Till 3-dimensional space. Physical space can all be 3-dimensional. Let us forget the orientation. Physical space is only 3-dimensional space. Okay, joint space becomes Cartesian. If I want to make the robot point, then what I should take care of to describe the robot? Theta 1, theta 2, theta 3, theta 4, theta 5, theta 6, up to theta 110 I have to specify. What is the dimension of my task configuration space now? 10. Original problem was solving in 3-dimensional space. Now to simplify that, my space now is 10-dimensional space. Now imagine if you have to do optimizations or whatever it is, your problem becomes more complicated. This is the reason I am telling you this is, certain things simplify in some situation, but those same thing will complicate the problem in some other situation. Okay, so you can either work in configuration space or in as far as manipulator is concerned, configuration space and joint space are same. Okay, for a mobile robot, for a simple mobile robot, it is so. For humanoid, it becomes more, configuration space becomes more complicated. It depends on my entire body, right? Right. So if you consider aircraft, it is not axis symmetric shape, right? So maybe you will have a outer boundary as a configuration space. This is one possibility. But this is one important technique that we use both in motion planning or path planning problem and trajectory generation. The first thing is I want you to be very clear about what is motion, what is path, what is trajectory. Because if you just read papers, if you just read those things, this will not be clear. Okay, and I will also try to classify different motion planning problem based on these things, because these terminologies in technical papers, they are mixed up, they are messed up, and people, use everything for everything. Okay, fine. So I don't have so much time, so let me not get into this. I'll tell you these things. Okay, so what I will try to give in next around 5-10 minutes, I'll finish this portion. Okay, is that I only consider position and velocity, that is kinematics, right? But remember, okay, 5 minutes, or we will take the break now? Okay, we'll take the break now, we'll come back here, it's fine.